yesterday that I've been trying to, when I'm talking about multiphase, I'm also considering or trying to explain the single phase CFD so that you can appreciate multiphase more rather than talking only on multiphase, because single phase is a subset of multiphase. Okay, so we are trying to talk a little bit, and you should feel free to ask if you have a question about how to apply the code or what are the key elements in a single phase CFD calculation versus multi-phase. And I said multi-phase can be very complicated, so we will see how we do it. So then after today, we have 4 more lectures, and they are going to be on applications, as you already know. We will have bubble applications, which are quite complicated actually, droplet. If you want to go to the details of the physics, and then there is application on the cavitation, and then application on chemical combustion. So they all have different aspects of multiphase that we will cover. Okay. Any other question anybody has? So as I mentioned to you, yesterday, that today's presentation is full of numerics. So this is the only presentation that you will find that is full of numerics. The other one will be the use of the software to do application. So from today's lecture onwards, it will be all the use of the software. Okay. So for example, there will be some discussion which most of you know, that how do you solve the equation, right? So that is, many of you probably already know, simple algorithm is used. Anybody is not familiar? I think everybody in the audience is familiar about Fluent, right? Anybody not familiar? Okay. So I think that except a few people who may not be familiar, who are have a only mathematics background or physics and never used the software, so they may benefit a little bit more from today's presentation. How many of you know the numerical method behind VOF? Because in a multi-phase flow, VOF is one of the most important elements. How many of you know what is VO? I mean, you know volume of fluid, you know tube phases, but how do you know? Do you know the mathematics and the numerics behind it? Anybody who knows the mathematics and numerics behind the VOF, please raise your hand. So there is at least one person who knows the equations about VOF, right? How many of you know the level set method, the mathematics and the discretization behind it? So all those equations and how those differential equations are solved numerically, that also I am going to discuss, but not in so much detail that for that, if you want to go into the great detail, then you have to have a lot more time. So that is the goal today, is to give you some basics about the numerics. Okay. So everything is governed by the partial differential equation. Everything. And most of the partial differential equations that we will talk about, whether it's in the context of the multiphase like VOF or the level set, and also there are ways to combine the two. So that is what is called the combined VOF and multiphase. So it is also called the Watt method. Okay. So combined multiphase VOF, which stands for the V, and then the level set is SOT. So there are various versions of it. and there is not a single one way to solve the problem. Okay. So, like if you want to solve the incompressible flow problem, simple algorithm is not the only way. You take any book on CFD, there are many ways to use a numerical scheme that will solve the problem, right? What is the requirement of a numerical scheme to solve, let us say, the basic conservation equations of fluid mechanics: mass, momentum, and energy? So, what is the basic requirement of that scheme, numerical scheme? What are the basic requirement of that scheme? Huh? Uh-huh. Uh-huh. Yeah. Yeah. So there's a Lex equivalence theorem, and that, don't worry about the name, but the important thing is that discretization that you have should lead to a solution, and should lead to a unique and correct solution, right? But the solution, numerical solution, will always have some truncation error, and it can have some other sources of error due to the computer and other things. But basic numerical error by the Taylor series is the truncation error, right? So that's where your first order accurate scheme, second order accurate scheme, third order accurate scheme, that comes into play. That your discretization of a derivative has a truncation error of second order or first order. That is the order of the scheme. And consistency that he mentioned is that in the limit that the discretization stencil goes to 0, you should be able to retrieve the partial differential equation. So, it must be consistent, and the good news is that you don't have to worry about it, because 99.99% cases are consistent. But the important thing is that the scheme discretization should be such that eventually it should converge, and if you did not do it correctly, then it will not converge. So, fortunately, if you use the Fluent as a black box and you just say, I want a second order scheme and I want to have the steady state, or I want to have a simple algorithm, you just keep on clicking on those boxes and it will automatically take care of rest of this stuff. Okay. So, my goal here is to try to demystify some of the things that are built in the Fluent, and so I am going to describe something for which one of my students, he wrote his own code, a multiphase code, to be able to do things to investigate. Okay. So, that is what I am going to show you, that how you can do it, but it will be basically based on whatever you have in Fluent also, so that you can use it. So, I already have given you an interview, an overview, and so it is just a repeat. So, I am not going to go over all these slides, that you can read it on your own, and you already know the multiphase is a very complicated flow, and so experimentally as well as computationally. Computationally now is going to be much cheaper than the experiment. So, I think that is what we are going to be interested in, and I already classified for you what type of particle flows are: dilute flow, flow of solid and liquids. So, all these applications we will be talking about as we move on. So, some of it is a repeat. We are going to talk about fluidized beds towards the end of this course. So, some of this, you can read it, it is kind of repetition of what we have already done. Again, some of the terminology that we covered yesterday in lecture 3, including the dimensionless numbers. So, some of the numbers that I mentioned to you we will be using today. Reynolds number is the most important in whole of fluid mechanics for a single phase, multi-phase, and the other numbers that are important is the Morton number, the Bond's number, and the Weber number, depending on what the calculations are, and the cavitation number if it is a cavitating flow. So now I will try to not go over this, but the important thing again, if you remember we spent some time that there is a one-way interaction or there is a two-way interaction. That is a very important thing to remember when you are applying the code, or there is a four-way interaction. Okay. So suppose you have a particle, and I gave you the example of a nanofluid. In the classification of multiphase flow, what kind of interaction it was? It was a one-way interaction, which means that the particle of nanofluid, it was so small in percentage and so small in size, they were in Brownian motion, that when they were moving around, the only hydrodynamics was responsible for what is happening. But the hydrodynamics, the influence of hydrodynamics on the particle was not accounted for. The particle were influenced by the hydrodynamics. Okay. But the effect of hydrodynamics on the particle was not accounted for, because if you account for the effect of hydrodynamics, what is the most important quantity? Is it drag? So we did not include the drag at all. So it is a one-way interaction because the number of particles were small and 1 or 2%, 4%, and so we just treat it as a one-way, one single phase flow. For some applications I will show you, like if you have a cold particles moving into the air, then the hydrodynamics is exerting the force on the particle and the particles are influencing the hydrodynamics. So this becomes a two-way interaction. So both are mutually affecting each other. Okay. And if you have a liquid and liquid, which are say two different fluids like oil and water, then again the same thing. The liquids on each other are influencing via the interface transfer of momentum. So there is an interface transfer of momentum. So when you are considering the different phases, then in the momentum equation, if it is a two-way interaction, it must be reflected in the equation, which means that the effect influence of the particle should be in the equation. Okay. And if you are using a two fluid model, then you have two set of momentum equations. So both of them should have a term which is interacting term. Now then there is a four-way interaction. Anybody remembers what is a four-way interaction? So in a two-phase fluid you have a four-way interaction. So you have a hydrodynamics influencing the particle, and particle is influencing the hydrodynamics, but the particle is influencing the other friend of it, right? So that is the one becomes a four-way interaction. So that is the most complicated one. Now that can also occur if you have a multi-phase type of particles, I mean a set of more than two particles, but in the same type of particles also you can have four-way interaction. So we will be dealing in the entire formulation two-way interaction. Okay, we will not be dealing with the four-way interaction, although you can make more and more complications into it. Now if you use Fluent, it is only able to describe one way or two way. It also does not have the capability to do the four-way interaction. But if you have an application that requires four-way interaction, you will have to write a UDF that will describe that how the two particles they collide with each other, and then you will have to figure out it's an elastic collision or is an inelastic collision, and you can add on as much as you want. But most of the applications don't require that at all. So we will not be interested in that. And then of course, this thing is built in Fluent to some degree, not entirely. Evaporation, condensation, and combustion reaction. So that becomes a very complicated problem. That is, a phase change takes place simultaneously in the calculation. And of course, if the two kind of fluids are reacting with each other, or the solid is reacting with the fluid, then it becomes a more complicated problem. For example, if you have a coal combustion, then the coal particle will interact with the oxygen of the air, and at a temperature of 8 to 900 degrees centigrade, it is going to burn, right? And if it is going to burn, then of course you have a combustion that is taking place, and this you will have a formation of steam and carbon dioxide. So, to account for that development in time, you have to have a time dependent calculation. You can do it with fluent, it becomes a more complicated problem. So, all these things is built in, but what is the method behind it, that is what we are going to discuss. So, as I already told you, in our first lecture on the introduction, that there is a method which is the most simple method. What was that? What is the name of that? ASM. So, that is the most simple one, but nobody should use that anymore, right? Because it is too simple to calculate any of these things in a reasonable way. That method was okay in 70s and 60s. Now, there are two methods that we are going to be discussing in depth in this course later on also, and one is the Eulerian method. And Eulerian method means that you are basically not tracking the particle, even if there are particles like nanoparticles in which there was only one-way interaction. You are not trying to see, even in a two-way interaction, that what is happening in terms of the particle behavior. So, what we are going to assume is, from the kinetic theory of granular flow, that the second phase also behaves like a fluid. So, you call it a two-fluid model, although the second phase has solid particles. But the calculation becomes extremely simple. Now, if you have to track all the particles simultaneously, that becomes an Euler-Lagrangian method, which is more accurate. But the problem there is that if suppose you have number of coal particles, let us say you are studying combustion, they could be in billions, at least in millions, and that is a very large number. And the law of governing the motion of those particles is very simple. The law of governing of the motion is the mass times acceleration of the particle is equal to the force. That force is, of course, comes from the hydrodynamics. So, that has a drag law, that has a lift force, that can have gravitational force. There are about 6 or 7 types of forces that a particle will experience. So, that becomes a two-way interaction, but to chase those particles in a Lagrangian approach is a very very time consuming. It may require high performance computing and all that. So, there are now solutions to address that problem, and that is, I mentioned to you, there is a partial approach that you can use to get a reasonable answer by having a lesser number of particles. So, we will talk about that. Now, whether you are doing the Eulerian approach or you are doing the the Eulerian-Lagrangian approach, the interface has to be captured, or you have a stratified flow, or you have a water air interface has to be captured. So, there are three methods that are there right now: the front tracking method, the volume of fluid method VOF, which is very popular, and the other one is a level set method that has only come along recently, and not many people are using it, but there are theory behind it that have been integrated in the fluent. So, I am going to talk about all these methods, the numerics and the theory behind these methods. Okay. All right. Okay. Then, as I said, you can have hybrid method, you can combine the level set with the VOF and so on. Okay. And of course, somebody had mentioned that about the lattice Boltzmann method. And then there is a method which has been developed, and some of you might have come across in some other applications, which is now also a part of Fluent. It was not there before. It is called grid-free method. So, in the context of the multiphase flow, this is called the smooth particle hydrodynamics, SPH, and it's also in Fluent. Okay, and if you want, you can use it in some cases. Lattice Boltzmann method is not a part of Fluent; it's not there, but people are writing a lot of research papers, a lot of work, and there is a company called EXA, and EXA has a software. It's very expensive. That has a lattice Boltzmann method for single multi-phase flows. Okay, so that is the only software that is using lattice Boltzmann method. It's very expensive. So I am not saying that you should be doing that, and I think that many of you to learn the simple lattice Boltzmann method will take you some time, unless somebody is offering a course in that area. So, but you should know that such a thing exists, because somebody had mentioned, just might have heard about it or something. So that is something, but we can discuss about hybrid method that you can use, and particle based method also is influent, but we are not going to talk about that, and we are not going to talk about the lattice Boltzmann method. So this is a simple simulation, just to show you some videos, to keep you a little bit awake and entertained. So what you see here is that there are about 18,000 particles here, okay, and they are just moving into a simple air. It's a very simple simulation. So this is a box, and so you have initial state at the bottom. You have injected these particles, so they were forming a bed, like a fluidized bed type of a thing, and then you just let the bed, you introduce some velocity like a fluidized bed, and then they will start moving. So it just basically shows that you can do this. It's a much more simple, I would say, example to see whether you are able to run the Fluent. There is no other purpose of this simulation. There is no physical significance except that you can run this simulation. And also it has some other significance, is that you can also use the visualization software, okay, which is not easy to use, by the way. And then you can create a video also. Some of you may be very good at it, but that also is a part of the whole learning process after you have done the calculation. So this is a very simple calculation. So what you have is, you can just take the standard equations, take this box and have a very coarse grid, and just inject the flow at slightly greater than some superficial velocity, and have a small bed and have it run, and you will just find that this is all moving up and down. So this basically shows that you can do this calculation, nothing more physical than that in this one. No, you can consider them as beats or whatever you want to call it. There is no reaction, there is nothing going on. It's just a simulation that you have bunch of particles that you have at the lower bed. I don't know how much it was. It may be 1/10 of 1/100th of the whole size of the height. You can, this is just a simulation, I mean, you can take a square box, whatever you like. You can take a cylinder. The idea here is that you inject the velocity into the air, and you have a bunch of particles. You can take 100 particles, you can take 1000 particles, and see if it works. It's not, this is basically Eulerian model. Okay, this is not a Lagrangian. This is basically Eulerian model, the most simple one. Okay, there is no interface, there is no VOF, there is no LS. It's just simply taking the model, running it on a square grid or a rectangular grid, trying to see whether it is working. So I am a preacher in this area, is that always take baby steps, go slow, all right. Don't look at the whole three-dimensional problem that somebody has assigned you, because if you cannot do this, then it will be very difficult to do the next step. Okay. I mean, if they were heavy and you had included the gravity, then you will have a different flow. Here these are some bunch of little particles to see whether they are able to interact with the hydrodynamics or not. And there is no force on the particles also. So this is a one-way interaction. Okay. So as I said, this is just a completely an exercise to see whether you can run the code. All right. And I think that this is very important. All right. Because I am telling you that when I have a new student and the person comes in and I say, this is the computer, and this is your desk and this is your password. Okay, I don't assign it, but somebody in the lab who maintains that assigns the password. And this is the fluent, and do the tutorials. They are not able to open the software and they don't know where to click what. So this is simply to initially to just know what it is in a multi-phase context. Okay, nothing more than that. We are not solving any problem at this point. Okay, so this is other a very interesting problem and I will come back to it. So here you see that I have introduced two dimensionless numbers, and I keep telling you that the entire fluid mechanics is based on some dimensional number or the other. And the most important one was the Reynolds number, then you guys mentioned the Mach number, and somebody mentioned some other number, I think. So there are, so one is a compressibility effect, the other one is a viscous effect, an inertia effect. So you have to explain the flow features in terms of a dimensionless number. So in this case, there are two numbers that are important. One is called the Morton number and the other one is called the Bond number. Okay. Now both of them have the gravity in this and both of them have the surface tension in this. So the surface tension and the gravity are the important phenomena, all right. I don't know anybody remembers, what these numbers are. I don't remember. Anybody remembers? And the third number that is very important is called the Weber's number. Let me see if I have a paper here. Otherwise, I don't want to go back to the. So the Morton number is given by the rho of the liquid minus rho of the gas. But if suppose it is air and water, it's 1000 to 1, you can not worry about the gas, all right. So it's basically density of the liquid times the gravity times the diameter of the bubble is square divided by surface tension. Okay. So surface tension forces plus the gravitational force. The other one is the bond number. No, this is the definition of the bond number, by the way. And the other one is the Morton number, which is G times the density of the liquid, not the bubble, to the power 4th times the density of the liquid divided by sigma to power cube. So anyway, that's not important. The important thing is that these are the two numbers and they are related to the Weber number. And so if you go back to our presentation number 3 or something like that, then you will find that all these are given. There are a lot of numbers, all right. They are difficult to remember because we don't deal with these numbers that often. So you see here the other thing is CR. CR is the confinement ratio. So, confinement ratio is the size of the initial bubble and the size of the channel. So, this is the width and this is the bubble. So, here the size of the diameter of the bubble and the width W over D is 4, and this T is some non-dimensional number. Okay, so you can have T some times U over D or something like that. So, this is just how the evolution is taking place in time, and this is again done by in the fluent, by the way. So, you see that a circular bubble, as it moving up under the influence of the gravity and rising up, effect of the surface tension is there, it changes the shape. And then of course, as you expect, there is a wake behind it, and it's like a sphere, moving into a pipe. So, you can do that, and it is a multi-phase flow. It's a liquid and the air, the water and the air, and the Morton number being very, very small, and as I told you, there's a complicated expression, and the bond number is high, 50. Okay, and but all of them, the surface tension and the other parameters are identical in definition. So, you are basically defining a flow at a high bond number. Many times people ignore the Morton number, because as you can see that the Morton number in this case is very, very small, and the bond number is the one that is important. So, you will see in the literature, like if you look at the book by Brennan, by the way, you can download the book by Brennan if you don't want to buy it, it's free. And so, you will find that he only mentions the bond number. They don't even mention the Morton number for this kind of a flow, because that is very small. And again, you can apply ANSYS by using the VOF, and can do this very easily, and this is a very straightforward grid, and you have to push in the velocity of the bubble, and that's it. And VOF is automatically to calculate the shape. Okay. Now, what is VOF? I mean, the people only one person seems to raise a hand that he knows the VOF. Okay. So, I'm going to talk about what exactly VOF is, and how do you discretize it, and what is inside the fluent. Okay, now this is the very interesting simulation, and what you have is again a box, and in this particular box you have a molten steel. The entire box contains a molten steel, and this is a bubble of air inside the steel. So, it is actually a liquid air multiphase flow. It's a model problem, but the difference in the density and difference in the property is very huge. And why this problem was interesting is, so it says a bubble steel interface, that blue line, bubble steel interface. So, this is the bubble at the bottom, and there is an interface here. So, interest here is that any time you do the casting, like I am sure that nowadays they don't teach it, but if you are from an older generation, then one of the requirements of mechanical engineering was that you have to take one semester of foundry. Now, people, I don't think I ever go to that place, which means that you have to learn how to create a steel ingot in foundry that you can use to make any product that you want. And one thing you don't want is that you have in that process of making this steel ingot, you have all these bubbles inside, and if you have all those bubbles inside trapped, it becomes weak. The strength of the steel can go down by a large number if you have these defects. Okay. So how do you remove that bubble? That used to be a big problem, all right. So I mean, I don't think, any of you, as I said, our multiphase, we are younger people or older people, okay, and the multiphase in this room is really a very kind of a dominant other phase, But I don't think anybody has has anybody of you have gone to foundry? You did it? We used to even do lathe machine. Anybody has done the lathe machine? Okay. How about the drafting? So looks like that you are not really a very, very young generation, Because I mean, I thought that all those things have disappeared because drafting, is a very painful thing. And now with the help of all this CAD software, I mean, to do the drafting is like, using a slide rule to calculate 2 times 2, right? Anybody has used a slide rule ever? You have used? Okay, must be you are a very curious person about this, I mean, I have tried to save this slide rule, because I thought it's a kind of antique. Okay, but then I found one day that it was all thrown away. The point I'm saying is that in a foundry area, it is a very important problem, but it's still, from the manufacturing point of view, those who are making steel, this is a very good problem. And of course, from simulation point of view, it is a very tough multi-phase problem. Now, how do you control that? In the old days, there were many of other methods that how do you control this bubble formation. But now they found out that if you apply the magnetic field, then you can control the size of the bubbles. And of course, how do you apply the magnetic field is that only if there is a current going on inside the steel. So current means that you apply the electrodes, and steel is a very, very good conductor of electricity. It is as good, may not be exactly as good, but is as good as copper. If you don't believe it, you take a wire of steel and try it out. All right, you will then, I mean, it's like, somebody, said that, small kid said, father said that don't go near the fire, If you put a hand on the fire, you will, no, I mean, you can get burned. And the kid never believed his father, He said, he always talks nonsense. So he went and tried it out. For the first time, he realized his father sometimes speaks the truth. But this is really something that has been a very important problem, so we tried it. Unfortunately, these videos are not working. So what you see here is there is a 3 millimeter ball, very small ball of bubble, which represents a bubble, and B is the magnetic field in Tesla. That is the unit of the magnetic field. So there is a magnetic field that is applied in 0 Tesla, 2 Tesla, 3 Tesla, and so on. And this is a smaller bubble of 3 millimeter, then this is a bigger bubble. Although they look the same, but actually they are bigger in size in actual calculation. So now this is what really happens. So what you see is that if you calculate the vorticity, and this is the top direction, this is this direction, and this is the bubble, and you can see that at the 0 Tesla, at 0.2 Tesla of magnetic field, and this is 0.5 Tesla, and the magnetic field is applied in this direction, and the electric is this direction. They always are normal to each other. If you don't know, they are like a potential and streamline. Those of you who know fluid mechanics, you know that the potential lines are always normal to the streamlines. So similarly, the electric field is, at least in axisymmetric case, is always normal to the magnetic field. So in this case, the electrodes are going like this, so current is going like this, and so the magnetic field is perpendicular over the on this screen or on the board. But what you see here, which is more important, is that as you increase the magnetic field, you can see that the size of the bubble as is rising through the medium of the molten steel has become very small. So they have found that actually by there is not, this is just a very simple modeling, but in general, there are hundreds and hundreds of thousands of bubbles there. So by applying the magnetic field, you can control them. So now the manufacturers are using this method. So this is just to show you there's a two-phase flow, and you can do it by fluent. So even though there is a large variation in the density of the two, very large variation, and the surface tension is very different, because the bubble is air and the other side is, water is 1000 times the air. This could be 1,000,000 times the air. Density is so large, but still you can do these simulations if you do it carefully, and you can do it by using fluent. Now this is another view for a 7 millimeter bubble. That was a 3 millimeter bubble, and again you can see that as you change the field, magnetic field, so you can see that there's tremendous impact. All right, these are all blown up pictures, but in the actual practice, when you have a large number of little bubbles, it does seem to make a difference. Okay, this is one example. Now let me show you another example. Now in this case, we have a real example that was done again with fluent. 860 air bubbles along this rectangular water column. Size of the domain is 48 millimeters square. Height is 192 millimeters. The grid is 32 million nodes. Okay. Don't be scared, actually. You can do it on your laptop. Okay. Your laptop, you can do this. And then you have, of course, walls, which are periodic. And then the size of the bubble is 2 millimeters. And the Reynolds number, there are two of them that come into play. One is the bulk Reynolds number, which is based on the width of 48 millimeter here. And then you have the bubble diameter 216, which is like a very, very small number. And this is this. All right. So now, again you do the calculation. Fortunately, these videos are working actually. Some of them are still not working, but I tried to make it work as many as I could. So what is interesting to note here is a front view of the bubble motion, there is a top view. And then you have, after a certain time, it is just we stop the calculation. So if you go here and you go here, and then you eventually, after you stop the calculation, you go here and here at a certain time. Okay. What do you notice? What is happening to these bubbles? Anybody can notice? Most of them have now lined up along the wall. And then in the middle, they have removed. So total number of bubble is the same. But what has happened is that they are not bursting or anything. We are not considering that phenomena. But they are all lined up here. Okay. So the flow pattern has completely changed for the flow conditions that we are using. And this again, you can do this kind of a calculation again from fluent. Okay. All right. And this all have used only one method, and that is VOF, volume of fluid, which means that between the bubble and the neighboring fluid, the phase change, not the phase change, but the change between the gas and the liquid, you can calculate by the volume fraction, VOF. Okay, the other thing, this is an interesting one that you can have more complication. And what you see here is that there is a square duct and this is unladen and laden flow. So what is the meaning? You know what is the meaning of laden and unladen flow? So one of them has particles and one of them doesn't. Okay. So what you find is that in a channel which is means a very large aspect ratio, is like a channel, and the other one is like a duct. But what you find is the difference in the unladen and laden flow is that if you have a laden flow, which means the particles are there, then the behavior of the bubbles can be totally changed. Okay. So you can see that you can completely change the physics in case of the formation of steel ingots and removing the bubbles. So it's a very practical and important problem that you can figure out with the simulation. All right. So it has a lot of merit. And the other case, you can see that you can sprinkle a few randomly some particles to make the flow laden flow, and those particles can make the change in the bubble inside the flow completely different. So all these are practical effects depending on the application that you're looking at. Okay. This is again a calculation in which you have the electromagnetic braking, and so you can again see that these are the actual bubble size in the simulation, and they are literally in millions, and you have again the magnetic field of 0.1 Tesla and 0.2 Tesla, and the bubbles of different size. And you can see that the way the bubble is spread in the domain, this is one of the front views, can be totally changed if you apply the magnetic field. So in all these applications, you can see that they are practical applications of multi-phase flow. All right, but these are model problems, but still, they are quite compute intensive. This EMBR is electromagnetic breakdown means that. So this is actually a problem in the flow control. So this is a flow control, that is the control of the bubble by applying the magnetic field. And so the flow control in this context is called the electromagnetic braking. But this also you can call is a flow control of the bubble inside enclosure, so that you can restrict them in a certain fashion. So this is another example. So I think that these are the motivational examples that how in various applications you can do some really useful things. I showed you a few of them, and you have to, they are all done with the help of Fluent. Now, by the way, few years back, Fluent did not have the capability of magnetohydrodynamics, and so you couldn't do it, the calculations that require electric and magnetic field, but now they have it. So as they are building up the capability, you can do it. Okay. So somebody was asking me today that can I do all this in the open form, not what I am showing you. And I said you can do anything you want. I mean, you can start from scratch and build up the code. All right. It depends on how much time do you have and what your motivation is. I mean, people can do anything they want, but do remember that there are certain limitations, that there are only 24 hours in a day, and you have to eat, you have to sleep, right? And you have other commitments too, and then you can calculate how much time it will take, and then after that you can see that how many times you have to be born to get it all done. So, yeah, yeah, yeah. The molten steel, the problem, you have to apply the electrodes, you have to have the current, and then you have to apply the magnetic field. So you have to include the Lorentz forces into the momentum equation. Oh yes. No, no. What you have to do is that when you write down the momentum equation, you have to add the Lorentz force if it is not there. But there are equations in the fluent which already have the Lorentz force. And then you basically see whether the kind of multiphase that you are doing, it fits in. If it doesn't fit in, then you can just write a small UDF and take care of it. But actually, it is already there, so you can do it. Now, you can neglect the magnetic field if it is very small, but then you are not doing what you need to do in basically trying to see whether you can really reduce the spread of those bubbles inside the domain. So, it depends on what your objective is. Now, by the way, let me tell you that there are papers in the literature in which the nanoparticles, what they call is a magnetic nanoparticle. So, you can actually use the magnetic nanoparticles and put them into the flow and then apply the magnetic field. But it depends on what the application is. If you are going to use to enhance the heat transfer in a radiator, you are not going to do that, right? Or if you are going to use in a refrigerator, you are not going to do that. So, it depends on what the application is. Yeah, so right now focus on what you are doing, and in the future if the opportunity comes and it makes sense, then you can think about it, what is needed. But the capability is there in the Fluent. Yes, yeah, yeah. You can add as many complications as you want from externally. The only thing is that magnetic field influences the features of the flow, but the theory behind the multiphase has nothing to do with it. It is additional force, you can say. Now, it might be possible when you non-dimensionalize the equations, that it might possible that there may be some other parameter may come up, which has some surface tension or some other thing, and if you don't know the name of that parameter, what is your name? Huh? So, then we will call Sharma parameter, all right. So, that will be Sharma number, that may be something you may like to look into. So, now what we are going to do is we are going to completely focus on the numerics. So, you are already familiar with uh, the simple algorithm, and so I am going to talk about which is more like a simple algorithm. So, this is the equations, right. So, these are the equations in 2 dimensions. To keep the idea simple, that is why I will not use the 3-dimensional equations, and in this case rho is not constant, we are leaving the rho. But one of the reasons that we are not keeping the rho constant is that when you are going to talk about VOF, then at the interface the density changes. Just like that the steel, the problem of steel, the density changes tremendously. In case of air and water, it changes by a factor of 1,000. Other cases can change a lot. So, we might need this help of keeping the density as a variable. So, these are the equations that you all know, the conservation of mass and momentum in Cartesian system, all right. So, now how do you solve these equations in Fluent? What is the discretization that you use in simple algorithm? Hmm? What? Yeah. So, what collocated is one, and what is the other one? Staggered. So you have both the possibilities. You can use a collocated one and you can use a staggered one. Okay, and both of them have a basically similar philosophy. The way you discretize the pressure term. So the pressure term derives, if the pressure term is dp dx, that is a nodal point, right? And in between the two nodes is the velocity in the x direction, and that is causes the staggered grid. If you have a dp dy, then the nodal points are pressure and the velocity in the y direction is in the middle at j plus half and j minus half, right? So that is the way the staggered grid works. And the nodal, the advantage of collocated grids is that you don't have to worry about this staggered arrangement. So those of you have not taken a basic course in CFD or have not been familiar or have forgotten, it is you can look back, but this is what it is. This is a very fundamental algorithm that is applied. Now the trick here is that you can apply it to the bottom two equations first, and then when you apply it to this continuity equation, then it turns out that you might run into some error. So then this perturbation of the pressure, when you put it in terms of the velocity field, it becomes a Poissonic quotient for pressure. So I mean, I cannot go too much in detail. So we are going to have the collocated storage algorithm, and then we can later on see that we can also use the staggered grid arrangement. Okay. So I don't want to spend too much time here, but let me ask, because all of you know about Fluent, that how many of you have ever discretized in your course in CFD or anywhere even single one-dimensional equation using a staggered grid? Can you raise your hand at how many of you taken a one-dimensional problem and applied the Pattankar-Spalding staggered grid algorithm? So there's only 3 people. That Pattankar-Spalding algorithm, or the simple algorithm that everybody has heard the name simple, right? What is the mystery behind that simple? That's what I'm saying. If you take the one-dimensional problem, you can see how to do it, and that discretization will not take you more than 5 minutes. Okay. Now, if you want to look at, there is a book by Pattankar. I don't remember the title, some computational fluid dynamics or something. If you take that book, there are examples of one-dimensional problem that you can try, one-dimensional analog of the Navier-Stokes equation. Okay, so what happens here is that we just, I showed you the continuity equation, so this has these terms here, and I will not bore you, because I think if I continue with this, then a lot of you are not even familiar with it and you will wonder what it is. So then this staggered grid arrangement, what happens is, let me see if there is a blackboard to just explain to you quickly. So if you have a one-dimensional problem or three-dimensional problem, and suppose this is your mesh. So this is a one-dimensional. So this is a simple uniform mesh, and so the one-dimensional analog will become for momentum equation without pressure term. You can add the viscosity if you want. Okay, this is the one-dimensional momentum equation. All right. The one-dimensional continuity equation will be simply this. So you can try to apply the Pattankar-Spalding algorithm here. The main thing here to remember is that the pressure is calculated at the grid points. and the velocity is calculated here. So the velocity is driven by this pressure difference. And in the y direction, the same thing happens. Z direction is the same thing happens. So you can take these equations and write it down for the conservation of mass, conservation of momentum, and you will find that put it all together, you will have a algorithm. And there are some other nuances. It is, I mean, there are some small other details, and that is the staggered grid. So the staggered grid means that the grid on which the pressure is defined is the actual grid, and the other one where the velocity is defined is not a actual grid. It is the one that you have numerically created for the convenience, so that, and then either u I minus half, you can later on take care of it. And what you do is that you can just simply take care of this later on after you have written the algorithm as this. Okay. So you can work it out, and as I said, if I mean, this algorithm is so famous that I think if you go on Wikipedia, it is written there. And this is the simple algorithm. Okay. Simple stands for something, but the thing is that if you want to experiment it, and many of you have not taken a course in CFD or want to learn yourself, you can take the book of Patankar, or you can take any other book and just go over that section, and it's relatively straightforward. And this is done in Fluent, and by the time you do in 3 dimensions and you put it together, that things become really complicated, but in terms of the principle behind it is straightforward. Okay. And it has been applied to many other fields, I mean, other than fluids. Now these are all the equations that I am showing you, but I don't think that's important, because a lot of you will feel bored that we are defining these parameters. So these are the 4 elements of the conservation of mass equation, that rho u and rho v, and defined at the middle point, which I showed you in 1 dimension. And so this becomes the conservation of mass equation. Okay. So middle point, I plus half, I minus half, j plus half, and j minus half in x and y direction. So I am trying to give you this information, not to bore you, but just to tell you that what is inside the code. All right. It has nothing to do with the multiphase. And now you can go to the momentum equation, and you can do the same thing. So x plus means I plus half comma j, x minus means that I minus half comma j. It is just written for brevity so that you don't write too much here, but it is basically that is what it is. So the x plus is the I plus half comma j, and x minus is I minus half comma j. So you can do all this. I mean, it doesn't take that long actually to do it. But once you put it together, then what are you going to get? You are going to get a large number of algebraic equations. So if I goes from, let us say, even for a rectangular grid or a square grid or cubic grid, whatever it is in 1, 2, 3 dimensions, then if I is 100, if there are 100 points in that direction, 100 points in that y direction, 100 points in the other direction, then 100, 100, 100, it becomes 1 million. So we will have a 1 million grid points. So how many equations there will you have? 1 million. All right. So how many of you can solve those 1 million equations? If you do the old fashioned way that you learned in 5th grade, all right, and how many years it will take you to do it. You will not be able to do it at all. You know, I cannot solve a 4 by 4 matrix. The point I am saying is that all the partial differential equations have reduced into algebra, and now you have to figure out how to solve the algebra. Okay. And there are easier way to solve the algebra. I mean, people have been doing with 30 million grid points, 100 million grid points. So that becomes a separate problem. So the fluent has a number of options, that how do you solve this algebra. So from partial differential equation, you have got the algebra or algebraic equation, and now there are options to solve the algebraic equation. But if you don't have a fluent, you can do it yourself, because there are a lot of libraries, a lot of methods you can. So you can write your own code to do this. Okay. Now, after you have done all this, then of course you have to use the boundary conditions. You have suppose put that one in. Then you have to make sure of one thing, that whatever method do you use should converge, should give a solution, because otherwise all your labor will go down the drain. So your labor should be such that eventually it leads to a good solution. So that is where the whole understanding of the stability, and he likes consistency. So consistency, stability, that means convergence is important. So there is a theorem which says that if a algorithm is consistent and stable, it will lead to convergence. Yeah. No, you can combine all of them. You see, yeah, you can. You see, this is something you have to decide. That is a separate field. You don't have to solve all of them the way we am talking about. You don't have to combine all of them as if they are together. You can do one by one. So you can first solve by assuming some approximate value, you can solve the conservation of mass. Then you can solve the next one, and then the next one, and the next one. That is the simplest way to write the code. If you combine all of them together, it will become an implicit problem, and then you have to invert a matrix, for which also there are methods, various methods which can invert the matrix more easily. Yeah. First of all, I want to caution you here. Okay. I mean, I can answer your question. Don't think that I don't know the answer. I don't want people to digress from the main focus here. Okay. So now if you bring the structure also, that is the equations of elasticity into picture, then you may like to include the equations of plasticity into the picture, and then you have a very different model like Nastran code. You are not going to write your own code, then we are really going on a tangent. Okay. So I want you to focus on multi-phase. And so in multi-phase, if you have a two fluid model, right, which I am going to talk about, then instead of having three momentum equations for one fluid and one continuity equation for another fluid, you have, and then if it is a heat transfer, then you have one energy equation for one fluid. So you, how many are there? 4 plus 1, 5, right? 5 equations. And if you have a turbulence, then you may have two more equations, 7. And if you have two fluids, you have 14 equations, right? And then you have a VOF, so you have another equation. So you may have already so many equations to solve, but you can do it. In principle, there is no limitation not to do it. Okay. The limitation is that what is the best way to get the answer, and that is the right answer. That is the limitation. But people have worked it all out. It is all there for you. You are born at a time that it is all there. But if you had to start in 1970, a person like me, everything had to be started from scratch, a little. But now in 40 years, we have so much knowledge that everything is in these codes. You can do it. The purpose I am doing this thing here is that not to teach you this, but to tell you a little bit so that you can appreciate what is inside the fluent. And this is not the only method. There are mathematicians and there are computational mathematicians who have spent all their life to figure out how to do this calculation fast. So what Fluent or CFX or any other code does is, whenever they come to know that something new has come in, they assign a person to do that and make it faster. Okay. But even if you have a structural thing, you can combine it. Okay. But the reason I didn't want to address it, that if you want to use a standard code like Nastran, okay, the philosophy behind the numerical method in Nastran is totally different than what we are talking about. So you cannot combine an apple and orange. Okay. All right. So that is but there is a way to combine it. That is, do this and then go there and then have an interface. Okay. So I think that most important thing is that I don't want to go over all this, without any benefit. If you are bored, just let me know. I am happy to, stop it. I am not saying, that I am, anyway uneasy or upset. My main purpose is that I thought that it might be beneficial to a lot of people who only use Fluent, and most of you have, except a few people who are probably have not seen it, maybe 5 or 6 people, that at least a little bit what is happening. Okay. So that is the purpose here. Anybody has any other question or comment? Feel free to have a question. Don't be concerned about that. Okay. So the momentum equation basically takes this form. So the other one you saw, now you have this thing here. So you will have these equations of this type. So you have a convection term, and then of course momentum is a little more complicated. Then you will have a viscous term, but as I told you that these middle of these guys, I plus half is nothing but average, just like I wrote down here. So eventually everything is on the grid. You see, this is something I want to mention to you, that this is our grid, this small little I minus 1, and this is our main grid that you generate by ICEM. These other things are artificial, and those artificiality are eliminated by this definition. So everything that you have is on the grid, but why you have to do that algorithm in that way that I am telling you? If you do not do that way, that the velocity in the x direction is driven by the pressure, in the y direction is driven by the pressure gradient in the y direction, then what will happen is that you will get a algorithm or a numerical scheme which will not work. Okay. Why it will not work is what is called is the odd even decoupling, which means that you will have a two set of equations which will not be coupled together, and that will be a disaster because you want to keep them coupled. So that is why you introduce this staggered grid or collocated method. Okay, now this might be, if you have never seen this or never heard this before, never taken a course in CFD, it might be too much. So, let's not worry too much, but I think that there are reasons behind everything that is being done. Okay. So there are reasons behind the technology or CFD building blocks that are being used. Now on top of this, suppose you did all this, what I told you, the staggered grid. It turns out that still you have a problem. that solution may not converge, particularly the convection. So physically what happens in a fluid? Suppose you have a fluid, physically what happens? You touch it. The moment you touch it, it starts moving. Okay, like water, air you cannot see actually, unfortunately, which is a good thing. You know, it's easier to see in air than in water if you know. So the fluid is start flowing with a little pressure, almost negligible. But you hit this thing, it doesn't flow. It's very hard, you know, because it is solid. So what happens is that because it is so deformable, that is governed by the convection part of the Navier-Stokes equation. So which means that the convection means the movement is so sensitive and deforms so large that the algorithm or the numerical scheme that we have set can still not able to capture that and diverges. So in order to solve that problem, there is a word that is used in the CFD literature is called upwinding. So what upwinding does is that if you make these changes that I am showing you here about those coefficients that are, you know, written in terms of complicated things, that you make these changes, then it turns out that you can hope to keep them converged. Okay, and most of the time they do converge, except under some very rare situations. So the goal here is that whatever we are doing, eventually we want to get a solution. Okay. Now there are still there may be problem. You will get a solution, but it may not be as accurate as you want. So that is where these issues of grid independence and other things, the order of accuracy of the scheme and all these things come into play. So now we have these equations which in a partial differential form, and what I am trying to convey is, if you want to write the bullets, is that take these partial differential equations, write down so that let us say they are second order accurate, just that is good enough, let us say, on some grid. Then what you want to assure is that the convection terms are upwinded, okay, in a more simple way. And then you want to assure is that once you have done all this algorithm, then you have to figure out how to solve the algebra. And let us say that keep it simple, so you do 1, 1, 1, 1, 1, 1 by 1 by 1 by 1. And then hopefully everything else will converge if you have done it right. But even then you have to be careful, because there will be a condition under which only it will convert. Okay. So it means is that suppose you have this much and you want to do it fast, and you say I am going to divide into only 4 parts and I am going to be happy. It may not converge because may be violating some condition, which is called the convergence conditions or the CFL conditions and so on and so forth. Okay. So that is the main thing that you should learn from whatever description I have given you. Now what happens here is that it is like this: you have a circle, right, and somebody wants you to approximate that circle. Okay. How many minimum number of points you need to approximate a circle? So no, the minimum number of points that you need to approximate a circle is 3. So if you let us say approximate with a 3, what are you going to get? You are going to get a triangle. If you approximate with a 4, you are going to get a square. If you approximate with 6, you are going to get a hexagon. If you approximate with 8, you are going to octagon, right? If you approximate with 10, what do you get? What is his name? I don't know. But anyway, so if you approximate by 100, then you will get very close to the sphere. So similarly, when you are choosing, you have this algorithm, you choose a mesh so that you can get a reasonably good answer, and that comes with the experience. So if you have done some of these calculations, you have spent some time, you have done some tutorials in the Fluent, I think you will get some experience, and you should use that and see if you can, learn this. So all these things, that I am saying, whether it's a single phase or multi-phase, you have to use some experience to do this. Now, diffusion runs are simple, because what they do is that when, as I said, you apply a little force and the fluid flows. This is a convection phenomena, and the diffusion means that they are viscous, so they try to control the flow. All right, not that much, they are not that powerful, but they can at least try to control it. They are simple, there is a central difference, and they are very easy. So there is no upwinding at all here at all. So you can do this. Okay. So this is the pressure gradient. Again, you can do the way that I explained to you, and then because it's a time dependent algorithm, you can do the simple, or here I am showing you another one, which is a fractional step algorithm, which means that you have additional steps, and then you go through this process, and then ultimately you want to satisfy the conservation of mass in 2 dimensions. Okay. And that is where, the simple algorithm is the one that was a major step to do this. So I am not going to go into all these details, but what happens is that the calculation at n+1 time step is written in terms of pressure gradient, and when you plug it back into the continuity equations, it gives rise to the Poisson equation of pressure. So then what happens is that the conservation of mass equation becomes a Poisson equation for pressure. You calculate the pressure, you plug it back in it, you get this value because you have calculated this pressure. This is already known. You get this. You now go back to the momentum equations, calculate the next step, and then keep on repeating the cycle. So this is a basically idea, but there are a lot of tricks, as I told you, that you must be aware of to do this. So I think that this is good enough, the introduction, all right. And we have already killed a lot of time in doing that. But this is applicable to multi-phase flow. That is why it is important. There is nothing in multi-phase flow which is different except the addition of volume of fluid method and the level set method, if you want to use that. So additional complexity is there, additional number of equations is there, but they are all solved by the same method. So if you want to write your code in 1 dimension, you can do that, or 2 dimensions, you can do that by following this procedure. So first of all, you decide the grid, then of course you have a pressure equation to decide the pressure boundary condition, then you calculate the middle values u prime, v prime. I think always use explicit, that is easier. You can solve for these values from the momentum equation, go back to this equation, update the values, and then keep on going back and forth. So this is a simple algorithm. So all of you have heard of simple. This is what simple is, and you are using whether collocated grid or the staggered grid is the same thing. And this is again if you want to organize the code, again the same thing that I just showed you previous slide, that you can have a computational domain, have the grid, and then prescribe the solution and flow parameters. At t equal to 0, you prescribe the flow variables, then start the calculations the way I explained to you. First all the momentum equations, and then they are done at the midpoints, and then you plug that into the continuity equation in the form of pressure correction, and then go back to the loop, and then you can get the solution. Okay, so this is the next step, and that's it. All right. So this is a basic algorithm for solving the conservation equations, whether it's a single phase or multi-phase. All right. And in this case, when I am talking about the multiphase, I am talking about the Eulerian two fluid model, because both are fluid equations. I am not talking about putting in a cold particle in there. Okay. But the complication is there, because if you have air and water or some other things, then you have two fluids, which means that your number of equations is double. Okay. And so in fluent, you can only do two fluids. If you have three fluids, then you need a three set of equations, and that is not built into the fluent. But they are wise, there are hardly any problems of interest that require three fluids. Okay. So I think that this is a good time to go and have your coffee, and then we will go to because this is the heart of the multiphase, that how to do the VOF numerically.